So my name is JoannaRutkowska. I work for Cosing in Advanced Malware Labs, and my talk is about subverting Vista kernel for fun and profit. Okay, so let's go to the part number 2, which is about abusing SVM technology for creating undetectable malware. What we have today in rootkit field is that we have something I call invisibility by obscurity. For example, FU by Jamie Butler works by unlinking, or Futu, by unlinking some kernel objects from some kernel lists, which makes them unavailable for kernel. But once we know the algorithm, once we know the concept of the rootkit, we can always write a detector. Sometimes we have some problems with reliability of those detectors for some obscure reasons, for some different reasons. But usually, theoretically, it is once we know the concept, it's trivial to write a detector. So, for example, DeepDoor, the rootkit I presented half a year ago, modified some NDIS data structures, some function pointers inside data structures. But again, it was completely undetectable over the time. But again, once we know the concept, once we know which pointers are modified, we can detect it. And also, I believe that there is only finite number of ways how we can actually implement any given malware. Like if we consider network backdoor, there probably will be like 3 dozens of ways how we can do this, like hijacking NDIS code, hijacking NDIS pointers in many different ways, like we've seen in Alexander's presentation. We can do this in really, really different ways, but not infinite ways, not infinite number of ways. But anyway, once we know the concept, we can detect it, which is so boring. So now imagine a malware which doesn't rely on a concept to remain undetected, which cannot be undetected, which cannot be detected, even though its algorithm is known. So how it works? So it's made publicly available. And we can go even a step further and imagine malware which would be undetectable even if its code is made public. This is something which reminds me of a modern crypto. We know the crypto algorithms, but we cannot decrypt the message, right? The idea behind BluePill is to exploit SVM extensions of AMD. Actually, the idea is very similar to what Dino presented just a few hours ago, but he did it on Intel VT, and I did it on SVM. So the idea is to provide very thin hypervisor, which will control the OS, and hypervisor will be responsible for intercepting any interesting events. And which events will be interesting depends what actually we want to implement: keylogger, kernel backdoor, whatever. I'll tell you later why. I'll just show you a demo movie. So SVM is a set of instructions which can be used to implement virtual machines on AMD 64. And there's a MSR register which is called EFER, which is for many different things, but it has bit number 12. And this bit, when set to 1, enables SVM mode. It doesn't mean that once we enable this bit, we are becoming hypervisor. It just means that the SVM instructions are available for the processor. And you can find detailed reference in Architecture Programmers Manual, Volume 2. OK, so this is how SVM works. This is the official explanation of SVM. Can you see the cursor? Yeah? So first we have SVM disabled, so there is no notion of host or guest, but still we are the native machine here, right? We are executing some instructions. And then we decide to create a virtual machine. So first we create something which is called VMCB, Virtual Machine Control Block, which consists of 2 parts. One part is the state of the guest, and the other part is the control block. And the state contains information like RIP register, RSP register, segment registers, and all the other state which would be necessary to create virtual machine. And control block contains information about what kind of events you would like to intercept. For example, that you would like to intercept every call of SIDT instruction, or every debug exception, or every page fault exception, or whatever. There's a list of few dozens of events which we can intercept. So once we create this VMCB, once we fill it with our preferred values, we can call VM-run instruction. This is one assembler instruction. This instruction takes an implicit argument, which is the address of VMCB. And this instruction is similar to call, because it starts the execution of virtual machine, which now executes, just like it was a function, it executes until some event occurs, event which we would like to intercept. So let's say we wanted to intercept, I don't know, page fault exceptions. So the operating system here executes until a page fault exception occurs, for example, or debug exception occurs, or somebody issued SIDT instruction, whatever, and then we break into hypervisor and we continue execution from the next instruction after VM-run, just like if it was a call instruction, generalized call instruction. And we call, from this on, we call this hypervisor and we call this guest. Okay, I think this should be obvious. And this is how Pacifica works, and this is how Intel VTX works. And now we have the slides, which is the most important slide during this presentation. This is how BluePill works. So again, we start here. This is our native operating system. Let's say it's Vista. So it is doing many different things, and suddenly it loads our BluePill code. And this BluePill code, at some point, well, let's say call a BluePill function. And this function does the following. It first enables SVM mode by setting this bit number 12, then prepares VMCB in a very tricky way. The tricky way is that we need to prepare it in such a way that this created VMCB, this created VM, this created virtual machine would be the same as the current operating system. So we try to clone our operating system into VM. So it requires some tricks. One of the tricks is that we make RIP. RIP is the 64-bit version of EIP register. We make it to point to the return instruction from this function. And then we call VM-run. VM-run creates virtual machine, and it starts executing from this address. So it starts executing from return. So it starts executing from here. So suddenly, we were here, we were the native operating system, we called this BluePill function, and we landed here, but we are now inside a virtual machine. And we continue executing. Let's say we have here like driver entry for our BluePill, and here we like have return status successful, and the operating system is doing something else, right? Switching to other processes, whatever. But now it executes inside virtual machine. And this here is the hypervisor, because we executed this instruction and we execute here. And let's say we wanted to have a keylogger. So we said that we want to intercept every interrupt. I don't remember what's the interrupt. Some keyboard interrupt. So it executes. Suddenly user presses key, and we have this intercept, and we land here. And here we have a big switch to see what event occurred. We do the appropriate action depending on the implementation, and we execute VM-run again, and we continue our operating system. So this is funny to notice that on this slide we had native operating system, which then became we had this native operating system, which then became hypervisor, and we had guest here, but here we have native operating system which became guest, and we had something which wanted to become guest but became a hypervisor actually. And the funny thing is that this operating system doesn't know that it actually became guest. This all happens on the fly. So we don't need to modify any boot sector. We don't need to take control before the operating system boots.